The sine function. Thanks for watching this video and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. Let's start with the unit circle. We see that the point P on the unit circle has coordinates x and y. The point P can move around the unit circle. The x-coordinate of P is cosine of theta, and the y-coordinate of P is sine of theta. So, as the point P goes around the circle, its y-coordinate is sine of theta. As the point P travels around the unit circle and moving in a counterclockwise direction, the theta angle increases. When the point P has made it all the way around the circle and back to the original point, then the new angle is 2 pi or 360 plus theta. Of course, the value of sine of theta is the same as theta plus 2 times pi. As the point P continues the second time around the circle, we get angles ranging from 2 times pi to 4 times pi. The values of sine of theta behave in such a way that values are repeated over and over. Every 360 or 2 times pi radians, the sine function repeats their values. This is known as periodic behavior. A function is called periodic if there is a number such that f of x equals f of x plus a for all x in the domain of the function. The least positive value of a for which f of x equals f of x plus a is called the period of the function. Sine is a periodic function of period 360 degrees or 2 pi. That's because sine is defined in terms of angles, and you can add multiples of 360 degrees or 2 times pi, and it does not change the angle. Therefore, the period of the sine function is 360 degrees or 2 times pi. We thus get correspondence between the y-coordinates of points on the unit circle and the values f of theta equals to sine of theta. The simplest way to understand the sine function is to use the unit circle. To graph the sine function, the horizontal axis shows the values of theta and the vertical axis shows the values of sine of theta. We project the values of sine of theta from the unit circle to the set of x to get the graph of f theta equals to sine of theta. It starts at the origin and moves up and down based on the values of sine. The sine of 0 radians is 0. The sine of pi over 6 is 0.5. The sine of pi over 2 is 1. So our graph hits 1 there. The sine of 5 pi over 6 is 0.5. The sine of pi is 0, so it's back to 0 there. The sine of 7 pi over 6 is minus 0.5. At 3 pi over 2, it is minus 1. The sine of 11 pi over 6 is minus 0.5. Then back up to 0 by 2 times pi, which is 1 full circle. Joining the dots as neatly as we can, we get a smooth curve. The graph is one period or cycle of the graph of the sine function. The sine function sometimes is called the sine wave. Like the waves in the ocean, it keeps going. the sine function can be continued beyond 2 pi. Let's see how the sine function works from 2 pi to 4 pi. As we learned previously, we can think of this angle as a full 2 pi rotation plus an additional pi over 6 radians. Therefore, 13 pi over 6 is coterminal with pi over 6, and so on. As we can see, the graph repeats itself every 360 degrees, or 2 pi radians. Feature of sine graph. The range of a function is the set of result values it can produce. The sine function has a maximum value of 1 and a minimum value of -1. Therefore, the sine function has a range that goes from -1 to +1. Domain. Theta represents all the angles in the domain of the sine function. We can rotate the point P as many times as we like. This means we can find the sine of any angle in degrees or radians, no matter how large. In other words, theta can be any real number. Therefore, the domain is the set of all real numbers. Period. The graph repeats itself every 360 degrees, or 2 times pi. Therefore, the period is 2 pi. Amplitude. The amplitude of the sine function is the distance between the horizontal axis, in this case the theta axis, to a maximum or minimum value. In this case, the amplitude is 1. We have just learned to draw the standard sine graph. We now consider some of the possible transformations that can be applied to the standard sine function, and look at how these transformations affect the basic properties of this graph. On the same set of axes, compare the graphs of g of theta and h of theta with f of theta. Let's make a table with the values of each function. The green graph is the standard sine function. We now draw the red graph. We can see that the red graph is twice as tall as was the green graph. The amplitude has changed from 1 in the green graph to 2 in the red, just as the multiplier in front of the sign changed from 1 to 2. We now draw the blue graph. We can see that the height of the blue graph is 1/2 the green graph. The amplitude has changed from 1 in the green graph to 1/2 the blue, just as the multiplier in front of the sign changed from 1 to 1/2. We can see that the number in front of the sine function changes the height of the graph. In other words, whatever number a is multiplied on the sine function gives us the amplitude of the function. On the same set of axes, compare the graphs of g of theta and h of theta with f of theta. Let's make a table with the values of each function. The green graph is the standard sine function, and it completes one cycle from 0 to 2 pi. We now draw the red graph. We can see that the red graph is squished in from the sides, as compared with the green graph, because the graph of g completes two cycles from 0 to 2 pi instead of one cycle. So the period of g is half the period of f. We now draw the blue graph. The blue graph is effectively stretched to twice the period of the green graph. If the angle theta is multiplied by a number greater than 1, as in the red graph, that speeds up the function, and the period will be smaller because it will not take as long for the function to start repeating itself. But if the angle theta is multiplied by a fraction between 0 and 1, as in the blue graph, that slows down the function, and the period is larger because it takes a longer time for the function to repeat itself. Anyway, we can see that the number in front of the theta angle changes the period of the function. If the number that multiplies the theta angle is b, so to get the period of the sine curve for any coefficient b, just divide 2 pi by the coefficient b to get the new period of the function. On the same set of axes, compare the graphs of g of theta and h of theta with f of theta. Let's make a table with the values of each function. The green graph is the standard sine function, and it completes one cycle from 0 to 2 pi. We now draw the red graph. We can see that the red graph is shifted over to the right by p over 6 radians, or 30 degrees. This relationship is always true. If we subtract or add another angle to the initial angle, the graph is moved in a horizontal direction from its normal position. In mathematics, a horizontal shift may also be referred to as a phase shift. We now draw the blue graph. We can see that the blue graph is shifted vertically upwards by 1 unit relative to the green graph. When a number is added or subtracted to a sine function, the graph is shifted upward or downward. Here is a summary of our findings from the previous investigations. The general sine function is the name given to any curve that can be written in the form: if k is positive, the shift is to the right, and if k is negative, the shift is to the left. This is known as horizontal translations. If c is positive, the shift is up, and if c is negative, the shift is down. This is known as vertical translations.